Is it okay? Okay, so hello everyone. Thank you for coming. I'm Olivier Ecart, and I've been working on DDS for almost 10 years now. And in this presentation, I will try to introduce this great but not well-known technology. So DDS stands for Data Distribution Service. It's a standard, and Eclipse Cyclone DDS is an implementation of this standard that we pushed recently to Eclipse. So in a recent Eclipse IoT survey, data collection has grown to become the second major concern in IoT. And I would even argue that it should be the first concern, because if you don't have the capacity to get the right data at the right place and at the right time to take the right decisions, then all your system is basically irrelevant. And I also think that data collection is a challenge that is a lot underestimated. And maybe this recent growth in concern can be explained because more and more people realize that it's not as simple as it looks like. Anyway, I think most of us agree that it's a major concern. Now, that being said, what are the characteristics, what are the properties data distribution system should have to fulfill the needs of IoT? Well, the main one is location transparency. So for historical reasons, we built our networks, our protocols, our systems, or internet, in fact, on the assumption that we would contact a host, contact a server, and then communicate one-to-one with it. And it's how IP addressing is based, it's how TCP works, and etc. But this is absolutely not how we use DDS today. I will use internet today. So we want to know what will be the weather in Toulouse tomorrow, or what is the temperature in room number 35, or I don't know what. But we don't want to care which server to contact to get this information. So this is the main property a good system should have. So recently, there have been a lot of debates here and there about which architecture between peer-to-peer and brokered architectures is the best to address and scale in IoT system. Well, we think that we need both of them. Indeed, when available, we should use peer-to-peer communications for performance purpose, availability, fault tolerance, and it would be a pity not to benefit from peer-to-peer when we can have it, when it is available. But when we need to scale out, then we need to move to brokered architectures. And we should make both of them working together. And it's typically how our networks work. If you think for a moment, in a LAN, we are kind of communicating peer-to-peer. But when we want to scale out and get out of the LAN, we need some IP routers, which can be considered as brokers in a sense. So we need something that can address both architectures, I think. Another key characteristic is time decoupling. A data publisher should be able to publish some data in the system and then leave the system. And a subscriber should be able to connect to the system and get this data afterward, right? Security is obviously also a concern in IoT in general, but in data sharing, data distribution as well. And interoperability is also key, because without interoperability, we won't have IoT. Right. So, what is Cyclone DDS? Obviously, you can imagine it's something that probably fulfill all the needs I just described. So, Cyclone DDS is a standard-based technology for ubiquitous, interoperable, secure, platform-independent, and real-time data sharing across network-connected devices. So, before we dive into what is DDS and how it works, we'll have a look at where DDS is used today. Smart grids. So, if you need to align your electricity signals, you need to distribute your data within 20 milliseconds. Oh, I must not hit this cable, I think. Peut-être qu'il faut que je le branche. Ok. Non. Je pense pas que ça vienne de la machine parce que ça continue alors que. Okay. Sorry for this interruption. So I was saying that if you want to align your electricity signals in a smart grid, you need to distribute your data with a periodicity of 20 milliseconds. And DDS is one of the technologies, if not the only one, that is able to do so at scale. DDS is also used in agriculture. So here you can see the example of smart green houses, but it's also used in cow milking robots, and also used, for example, in harvester machine that use DDS to synchronize with each other and collaborate smoothly on the field. Another example, so the Space Shuttle launch system uses 3 different technologies to gather all the telemetry, and DDS is one of these technologies. And I take the opportunity to try to show you how challenging IoT can be. So when you think about Twitter, the worldwide Twitter, we imagine it's something that's probably very hard to maintain and to make running smoothly, but they only have to deal with a few thousand messages per second, where in this case, in even quite basic factories, you have to distribute more than 100,000 data samples per second. If you fly in Europe, then your flight has been controlled with the help of DDS because Europe decided to use DDS and to impose DDS, by the way, to exchange flight plan between air traffic control centers. So smart factory, I started to talk about this already, but we know that OPC UA is majorly used in smart factories, but DDS takes more and more market parts in this area for several reasons, but its distributed architecture is one of the reasons. no decentralized. ELT is another example. So this telescope has to control his 100,000 mirrors to correct the diffraction due to atmosphere. And they tried several technologies, but DDS is the only one that were able to control those 100,000 mirrors 100 times per second. DDS is also used in medical devices and in robotics. So ROS2, the robot operating system, decided to use DDS as its data distribution layer. Right. Why are these applications using DDS? So we already partially answered the question regarding performance, latency, throughput, and so on. But let's dive into it. So DDS provides an extremely high-level abstraction. And when I say high, it even hides to the user the concept of messages. So it's really, really high-level abstraction. But this abstraction is built on a solid infrastructure that has already proven being performant, robust, etc. So, as I already said, building a distributed system is really hard. But building a fault-tolerant and scalable distributed system is even harder and underestimated, and a lot of people get it wrong. The abstraction DDS provides makes it easier to solve the problems, to address this challenge, and not to fall into the traps and fall pits distributed systems put in your way. And IoT systems will have to face a large variety of different environments. For example, it will have to face a large variety of different networks, from low bandwidth networks like 6LoWPAN or radio communications, up to LAN networks with high throughput and low latency, and also internet communications with their own set of problems. Also, IoT will have to face with a variety of different devices, like data centers, highly available data centers, but also tiny devices with megabytes of RAMs, and we are pushing it to fit into tiny devices with kilobytes of RAM. And DDS offers a unique abstraction to address all those different environments, different networks, and different kind of device and platforms, systems, and so on. So what is this famous abstraction that looks so great? Well, the main concept of the DDS abstraction is global data space. So in DDS, applications communicate with each other by simply writing and reading data from and to a global data space. So, and this concept gives us our wanted spatial and temporal decoupling. So, a writer application, for example, a temperature sensor, just want to publish the temperature it knows. Doesn't want to know to which server to push this data, where this data should be stored, what other application will need to read this data and when. And the same for reader applications that just want to get the temperature of room 35 and don't want to know where to get this information, where it is stored, when it has been published by who, etc., etc. But that said, if you don't want to have a big mess in your global data space, you need to organize your data. And the main concept to organize data are topics. A topic is defined by a mean of a name, a type, and some QoS. So the name is basically the identification of the topic. The type describes which kind of information, which kind of data are inside this topic. Does this topic contain temperatures, locations, luminosity? And what is quite unique is that topic DDS in general allows you to attach QoS to your data, so non-functional properties. It allows to define, attached to each data, its priority regarding to other data in the system, its lifespan, how long the system should maintain it. It allows to define the periodicity on which data should be available, and so on. So this aspect is one of the aspects that makes DDS quite complex for newcomers, but also it is very powerful and gives it its strength. So how does it work? Dynamic discovery is one of the aspects. So dynamic discovery is what allows to isolate applications from the underlying network topology. So this dynamic discovery is what allows application to just publish data or subscribe data without having to know where to push this data, which protocol to use, which transport, etc. Another key aspect is that this data space, that for now I draw like a unique cloud, is in fact decentralized, which brings two benefits. First of all, it avoids any single point of failure. There is no single broker or single server that, if killed, will make all the system fall apart. But it's also very good for performances because there is no bottleneck. And a third aspect is adaptive connectivity, and this is very key. So, for example, in a LAN, if a DDS publisher arises and the data it publishes should not be durable and there are no subscribers, nothing goes on the network at all. If a first subscriber arises, then DDS will establish a unicast communication between them, and the publisher will start to send data through unicast to the subscriber. If other subscriber arises, and all those subscribers are accessible through the same multicast address, then DDS will automatically switch to multicast and start to send the data through multicast without the application even noticing it. And finally, if suddenly some interest for this data appear in the cloud or in a device on internet, then DDS will start, as well as sending the data through multicasts, sending the data through TCP, for example, to a cloud or a subscriber DDS application or to a DDS broker. So without having to care about it, maybe your data will go through multicast, then through TCP, then back through multicast, and you don't have to care about it, which is really, really powerful. So DDS can run on a large variety of systems and platforms. Here are some examples. And it provides API bindings for a large variety of languages, which allows you to use it with your favorite language, but also allows you to build your application or parts of your different parts of your application with different languages, which is also very powerful. Right? Let's see a bit of code. So here is an example of a writer application written in Python, and this is not an example. This is code that really runs on some DDS users. So first, you need to define a topic by giving its name and its type. Then you need to create a writer attached to that topic. And finally, just write some data using this data writer. Pretty simple. Still in Python, a reader application, it's similar. Define the topic, define a reader attached to that topic, and what's new is that you can attach a listener to this data reader, and the listener will be notified each time new data is available. And when it is the case, simply read the data, and in this case, print it on the standard output. Okay? C++ now, it's a bit more verbose, because you need to go through the declaration of a domain participant and a publisher, but it's still quite simple. Here are the same in C++ for reading data. So I will not comment this in details. And we also have examples in Scala, which again I will not comment. But nothing very complex. Okay, so now what are our plans for the Cyclone DDS? So we want to make it simpler. So as you saw in the previous slide, here is a definition of the type of the data we publish and subscribe to DDS. And this type is described in a language called IDL, for Interface Definition Language, which allows you to define your type independently from the language you will use to read and write data. But you need to learn it. So we already have things to allow defining your type in your favorite language and don't have to learn IDL, but we want to push it to the community, which is not the case yet. DDS uses CDR to serialize data on the network, which CDR stands for Common Data Representation. Cyclone DDS also provides you with Google Protocol Buffer serialization, but we want to make this pluggable so that the user can use any serialization they want. We want also to, as I said, QoS is a part that is very powerful, but also a bit complex, because we have 21 of them, as far as I know. So we want to define some presets of QoS and some high-level concepts like state and events to simplify the life of the user. Then networking. So we are planning to add TSN support into Cyclone DDS. So TSN is time-sensitive networking. We also are already working on making Cyclone DDS supporting raw Ethernet, because this is something we saw more and more DDS users asking for it. And we also want to, so currently Rust2 uses OpenSplice as its default DDS implementation. And OpenSplice is the ancestor of Cyclone DDS. And so we want to push Cyclone to be the default implementation used by Rust2. So we are already working on DDS security. Before I speak about DDS security, I want you to know that you already have right now some level of security available in Cyclone DDS through TLS, but it's not standard, and it's kind of you are in or not in. If you have the certificate, you can get in the system, read and write data, and if you don't, you can't. But DDS security is a standard with far more fine-grained capacities. with access control, you can define if this or that application can read or write this data or not. And it allows you to encrypt only the user data or encrypt the metadata, the control plane data, let's say, or you can encrypt both with different keys, so that you only give the key to encrypt your control data to the infrastructure. So the infrastructure can route your DDS data, but can't see your actual user data, which is quite powerful. And so we are hardly working on it. It's our main concern right now. And this should be available before the end of the year. Now, what are our goals for the next years about Cyclone DDS? Well, DDS is for now still a niche technology. So this comes from the recent Eclipse IoT report I already spoke about. So yeah, DDS is still a niche technology because it's only used when needed. Yeah, people don't want to use a rocket launcher to kill a fly. But we believe that more and more IoT, industrial IoT, but also classic IoT application will need the kind of features I described and that are offered by DDS and not necessarily offered by other technologies. So we think that MQTT will still be the mainly used technology because it will still will be used when it fits. But our goal is to make sure that DDS becomes the de facto standard for applications that needs peer-to-peer, or the kind of scalability and time decoupling I described. And as we believe this will concern more and more IoT systems, then our goal is to make DDS the second used technology, data distribution technology, in the next years. All right, so you can find Eclipse Cyclone DDS here. Just a few words on other projects we are working on, and that also so FogOS is already in Eclipse. So FogOS is a system to deploy and maintain all kind of entities like virtual machines, native applications, unique kernels, and so on all the cloud to things continuum, including the edge. And if you want to know more about FogOS, there is a presentation in the end of the afternoon in which room? Sorry? In Diamant. In room Diamant. So I highly recommend you attend this one. And we also work on Zeno, which is a named data networking implementation. So as I told you in the beginning, more and more people reach to the same analysis that our current networking infrastructure based on I will speak to this server, I will speak to this machine is not relevant anymore. And so there is a new area called named data networking, which goal is to create a new kind of networks, not based on IP addresses, so machine addresses, but on data and named data. And I will access my data given a name. And Zeno is our implementation of such a network, low-level network, and could be one of the underlying transport implementation for Cyclone DDS. So that's it. Thank you for your attention. If you have any question. Yeah. I don't know the details about this, but TSN, do you already know TSN? Yeah, so on this aspect can give you a lot of details, but if you give me your contact, we can. Yeah, and to make sure that, as far as I understood, is to make sure that packets arrive in a certain delay to the other side.
Maybe I can find one version of it. We've been looking at that for a long time. Actually, in our open splice implementation that you mentioned, which is like the predecessor of Cyclone, we had embedded some network scheduling algorithms that are based on the available latency budget and the priority of the data. So one is about urgency, one is about importance, and those things we do in software, and we define multiple priority banks on the network with limited bandwidth, or there's very high priority data and less than short bandwidth. But we all do that in software, and this actually can still, on the real-time operating system, can get pretty good deterministic behavior. But with EFM, there's a really natural match, because EFM actually takes that same algorithms of scheduling based on importance and urgency, but drives that down to the wires and to the routers that are on your path to data. So we can make it very, very transparent, the use of EFM, because we can retain the QSs, the logical QSs that are already part of the DDS standard, which are transport priority and latency budget, so urgency and determination technology, and map those transparently without the user knowing that we are EFM ecosystem. So, and that's something that we've been looking at for a while, but it will happen now. There are some areas where EFM, well, yeah, I think even OCUA